This lecture will cover pretty briefly slope stabilization and repair. And the reason it'll be pretty brief is that we've spent a lot of time already analyzing slopes, so we know how to compute factors of safety and so forth. And once we know how to do that, it's pretty easy to evaluate the slope under new conditions. Maybe you've strengthened the slope, maybe you've decreased the slope angle, but the mechanics of figuring out whether the solution is going to work or not are already in place, so we don't really need to cover those. The thing is, though, you really do need to understand the cause of failure before you embark on any kind of mitigation plan or strategy. If you have an infinite slope kind of failure in cohesionless material, it wouldn't make a lot of sense to go and put in stabilizing drilled shafts or something like that, right? You might want to control the surface a little bit. That's a lot different than if you have a very deep existing landslide that you have to go and stabilize before you can build on there. And oftentimes it's really more than one issue that's at work in a particular landslide problem. So one problem could be that the strength of the soil within the slope itself is too low. You can increase the strength, you can decrease the slope angle. There's a lot of things you can do in those cases. A huge number of times seepage is problematic, so controlling groundwater may be the better option in that case, rather than focusing on a solution that increases strength or something like that. A lot of the seepage control measures are actually more economical than improving soil properties also. It may be that you have a problem with strength of the soil beneath the slope. For example, you're building an embankment on soft clay and you need to improve the strength of that clay before you can build the embankment or something like that. Or I mentioned already, you might have an existing deep-seated landslide. And those can be pretty tricky. Sometimes deep-seated landslides are huge and there's not really a whole lot we can do to stabilize them. So it's more of a risk assessment approach and maybe planning if there is slope movement in the future. So if the strength of the soil within the slope is a problem, here's a couple of solutions that could work. You might come on here and cut the top part of the slope and place it at the bottom of the slope as a fill. So this makes the slope less steep. It might improve your factor of safety to the point where you can tolerate that. The problem, of course, is that it's not always possible just to come in and cut and fill. You could have infrastructure here. Oftentimes there's a particular footprint that clients want. If this is a building project that, you're now taking away usable land. So this is not always an option. Instead of this geometry of cut and fill, you could also cut a bench and place a buttress, right? This has the benefit of decreasing the driving moment and increasing the resisting moment, even for a slope failure that goes beneath the areas where you're doing the excavation and placement of fill. You could always also excavate a much bigger zone and recompact it. That can be pretty expensive, right? This is a lot of work. So going in and cutting all that soil out and recompacting can be problematic. And if it's a natural slope, it's actually often difficult for us to compact soil denser than it already was. So you have to make sure that you're actually going to improve things by recompacting as fill. Okay, really commonly, seepage is a problem for us, right? We need to control groundwater. So here's a slope that has groundwater built up within the body of the slope. So if you're evaluating a failure surface, that might come something like this, right? You have high pore pressures over a pretty big range of the slope failure surface down here. And if you could lower that water table down, you could improve the factor of safety by removing those pore pressures and strengthening the soil. So one thing that's often done in these cases is to put in horizontal drains. So you would come in near the toe of the slope and just drill a hole back up into the slope like this. They're called horizontal drains, but often they're usually inclined a bit. And so here's the drain. It would be like a perforated PVC pipe that is wrapped in some sort of geosynthetic or something like that to prevent infiltration of soil. You just want to drain the water out. Well, the idea is that maybe the slope has pretty low permeability, and now you've put a high permeability path for the water to flow, and you can draw down the water like that. Maybe this is the before, and now this might be after, right? So then the water would get collected down here where it exits the drain, and would have to be disposed of in some way. So you have to worry about, how are you going to drain all that water off of the site. So these are horizontal drains. They're sometimes called hydroggers. And they're really, the size of the hydrogger is limited by how far can you drill back into the slope. It's going to require a specialty contractor to come drill these holes for you. But a couple 100 feet are definitely possible. All right, so another solution would be to change the direction of the drains, right? You could put in some vertical drains like this. You drill vertical holes in. Maybe there's some here too. And then the idea is that you could have a whole bunch of these. And also, I'm only drawing a two-dimensional sketch. You have to think of the out-of-plane dimension also. They have to be close enough together that you don't maintain a high water table in between the out-of-plane spacing of your drains. So the idea here is that you can pump water out of these drains, either lower a pump to the bottom and pump water out, or sometimes you can vacuum the water out too if the height is not too big and you're not reaching close to zero absolute pressure. And then, the idea is that you've now kind of created a new phreatic line that might look something like this in between these drains, and then back here it might keep going up back to where it was before. So we have new kind of before and after phreatic surfaces. And you might actually need more, right? Like in this case, you would still have a high water table there, so you might need another one right here at the toe, and then you can make this arc go more like that, right? And you've now removed water from the part of the slope that might fail. Maybe here's our trial failure surface is like this. I don't know what it would look like, but you've now reduced the height of the water. So we have before and after. Okay, the pumps may need to be operated quite frequently to keep water out. And again, you have to dispose of the water that comes out of those pumps in some way. So this would be a vertical drain solution. Okay, and these vertical drains are different from wick drains. You may be familiar with the concept of wick drains that are placed in soft clay to shorten the drainage path length and speed up consolidation. In the case of wick drains, the pump is actually whatever fill you place on top of the clay, because that pump increases pore pressure in the clay and therefore pushes the water toward those wick drains. In this case, simply drilling a vertical hole or installing wick drains wouldn't do anything, because you need to create a hydraulic gradient for the water to flow up, and so you do that using a pump or a vacuum. Okay, then there's also another concept that's related to kind of horizontal and vertical drains combined, and it would be to drill a pretty big drainage gallery, something large enough to fit equipment inside. So here's the drainage gallery. And this may be a solution that would be pretty expensive because you're drilling a tunnel basically, but if you just can't reach back there far enough with a hydrogger or something like that, you could drill this drainage gallery, and then you can come in and drill up some little holes to drain the water out into the drainage gallery and out. So that's another possible solution that was used, for example, at the Getty Center, the Getty Museum site. There's also a whole host of surface drainage techniques that you can use to prevent water from getting into the slope in the first place. You've probably seen a lot of these techniques on hillside slopes, near roadways and stuff like that. As you're driving, you'll see a little ditch that kind of zigzags back and forth across the slope. The idea is to catch all that water and dispose of it so it doesn't infiltrate into the slope and potentially raise the groundwater table. You could also use something like these finger drains, where you come in and excavate and put in some high permeability material to quickly get the water out and collect it in a tow ditch or drain here to get rid of the water. All right, then there are also structural solutions. These can be pretty expensive, and you shouldn't default into thinking of structural solutions. As engineers, this is often what we think of ahead of time: is what can we build that can hold this slope back? Well, usually dewatering is going to be less expensive than any kind of structural solution, so that's often the first thing we turn to. But there are times when you just can't avoid it. You need a structural solution. So one way to do that would be to construct a concrete cantilever wall. You would have to build a pretty big excavation just to build this footing. Here's the concrete pad that supports the wall, and it supports it for bearing capacity, but also for providing some extra weight, because now the weight of the soil that's compacted on top of that slab is helping to resist. It's like part of a gravity wall. So this would require a big excavation and then compaction and fill above that footing and behind the stem of the wall. It's important to always control seepage for these too. So a lot of the time we'll put holes in the bottom of the wall and some kind of drainage layer right on this side, geosynthetic or something like that, so that any water that does start building up behind this wall gets out before it puts hydrostatic pressure against the stem of the wall. So usually we'll put some kind of drainage, since we're doing a lot of compaction anyway. And this is a weep hole over here. And you might have seen these weep holes in walls, like if you're crossing under a bridge on on a roadway, say you're going underneath the 405 on Wilshire Boulevard or something like that. Take a look at those walls. You'll see little circular holes in the bottom. That's intended to let water out so it doesn't build up in there. So that's a cantilever wall. Sometimes we can't do all that excavation for a cantilever foundation. So maybe we would go with like a tie-back wall. That's where you would install some kind of a soldier pile. So you have to either drill or vibrate in or do something to get in a vertical pile. And then a hole is drilled back and a tendon is installed and grouted in place. And now, the failure mechanism might be like here, and that tieback is now grouted into stable ground behind. These are common in excavation situations where you're building subterranean levels of a building for parking or something else. But tiebacks can also be used without a soldier pile. Sometimes soil nails also, just on little pads that are placed on the slope to kind of anchor it back in. So there's all kinds of creative ways to use these things, and they are used in stabilization. We'll really focus quite a bit of attention on retaining walls and anchored excavations for the rest of the course. So I'm not going to spend a lot of time talking about these. We'll talk about how to design them. The question here is whether they're really suitable for a particular application. And then you always have to do a global stability analysis. Maybe the tiebacks are located within a slope and you have to analyze, is there going to be a failure that goes underneath them all the way around? All right, another thing that we'll do sometimes is stabilize slopes with drilled shafts. This may be especially useful for deep-seated existing landslides where there might be potential for movement of that landslide due to a future earthquake event or elevation of groundwater or something like that. So there's a landmass that has moved in the past. We want to prevent it from moving or minimize the movement in the future. But a lot of the time, the mass of moving land is just so big that our options are really limited in what we can do. We tend to favor drilled shafts for this instead of driven piles, because when you drive a pile, you create vibrations, and those vibrations can induce slope movements and things like that. So, we'll drill a hole in the ground, put a rebar cage in there, and then fill it up with concrete. And the idea is that some displacement is needed, right? So as the slope does start moving, now those drilled shafts are in there, and they're going to mobilize some resistance. If the slope never moves, all you've done is drill the shaft into the ground, and it's not really participating mechanically in any kind of stabilization. So for applications where you really have very low tolerance for displacement, this might not be a feasible option. just because you do need displacement to mobilize it. The other thing too that I will say is that some slope stability programs allow you to put a shear resistance for structural elements right on a particular location in the sliding plane. And it's tempting to say, okay, I know the cross-sectional area of this drilled shaft and I know the shear strength of concrete, so I'm going to compute that shear resistance to be equal to the cross-sectional area multiplied by the shear strength, right? That's really not appropriate at all. You may be significantly unconservative in that case and find that you can get away with very few drilled shafts to stabilize it. The problem is that drilled shafts typically deform in flexure. They're not going to just deform perfectly in shear like scissors cutting right at the sliding surface. As the slope starts moving, that drill shaft is going to bend over, and as a result, you're not going to get a huge shear mobilized at the sliding surface location until the shaft moves far enough and it's bending and deforming in flexure and things like that. So I just want to mention this because you don't want to fall into the trap of thinking that the full cross-sectional shear capacity of an included structural element is available to resist the loads. There may be cases where that's basically true, like if the soil's really strong and it's going to hold the shaft vertical and it's just pretty much shearing it along a distinct plane, then that would be like a rock bolt or socket or something like that. You can really get some resistance, but most of the time we're dealing with slender drilled shafts that are going to bend in flexure. So a way of analyzing this problem would be to do a lateral loaded pile problem. You can model the drilled shafts, for example, using the Winkler method. So here's a drilled shaft with a bunch of PY springs attached to it. And then a lot of the time we'll just impose some kind of loading condition at the head of a pile. We want to know its stiffness or its lateral capacity. And so we can put a displacement or a force at the top and figure that out. That's not what we do for this problem. What we do instead is we impose the displacement pattern on the pile that we anticipate, right? So we're going to impose some amount of displacement of the soil against the free ends of these PY elements and figure out how the pile interacts under that deformation pattern. So you're going to get some displacement like this, right? There's going to be curvature and bending of the drilled shaft. If it deformed in shear, you would have, kind of like a vertical one. All the deformation would happen right at that location. So that's not what's happening here. And that's why you get that reduction in shear force. Here's the subgrade reaction. That's like the line load acting on the drill shaft. And, it's generally going to be positive above or negative. It'll be the same sign above the sliding surface. Unless the shaft is really flexible, you might get oscillations up here too. But if it's stiff enough, you'll get kind of like the whole thing is helping to resist. You don't get load reversals. And then importantly, you can look at the shear force acting right at the sliding plane, right? So we can now relate the shear force on the sliding surface to the soil displacement at the ground surface and get a sense for what kind of shear resistance we can rely on for this shaft as a function of how much displacement we're going to tolerate. So you can do a shear on the sliding surface versus displacement plot like this. And that's called a pushover curve. It's important to include pile nonlinearity here, right? Usually these are going to be long piles, meaning that the pile will fail before the soil fails around the pile and flows around it. And so you'd want to put in some kind of nonlinear moment curvature behavior for the pile, and that'll influence the shear displacement relationship. And then you could say something like, well, I think it's okay if the slope displaces, 20 centimeters. So I'm going to come up here and that's the amount of shear that I have available for that shaft. And I can include that in my slope stability analysis. One thing to keep in mind too, when you do the pile analysis, shear would be actually for that pile, right? This is a 3D problem. So you're dealing with this single pile. In a slope stability problem, you're dealing with a cross-sectional slice per unit meter. So you would have to divide that shear by the out-of-plane spacing and convert it to like kilonewtons per meter, for example, instead. And that'll control the out-of-plane spacing of your drilled shafts. Okay, if you do have an earthquake problem, one thing you could do is run a Newmark sliding block analysis. And you could say if there's zero shear from the drilled shaft, if there's no structural solution at all, I'm expecting to get like this much deformation. And then as you add shear in there, you're going to get a higher and higher yield acceleration. So you might come along and get something like this. And eventually, if you add enough shear, you can get the yield acceleration to be equal to the anticipated ground displacement. So you come up with some kind of a curve that looks like this. That would be like a Newmark analysis for a seismic problem. Okay, one problem though is that when you do the Newmark analysis, usually you're assuming that the shear is acting the entire time during the entire duration of the ground motion. In reality, you're starting from zero displacement and moving to some amount of displacement by the end, and so that shear is going to ramp up as you go. So, one thing we might do is take the running average of the pushover curve, and then you can find the point of intersection. Sorry, I can't talk and write at the same time. The intersection would be your solution, right? This is your this is how much the slope is going to move, and then this is how much shear the piles are going to be under, so you can design them to accommodate that kind of demand. You can limit the deformations this way. All right, now there are other solutions. There's a whole host of ways of stabilizing slopes. You can do ground improvement. You can grout the slope. There's all sorts of different grouting you can do. You can do jet grouting. That's where you put a probe in the ground and erode the soil away and mix it up with a cement mix as you go and form a soil crete in situ. You can do permeation grouting. That's where you introduce a well and flow some kind of chemical agent in the pore space of the soil, and it will chemically grout the particles together, bond the particles together. Increasingly, people are using bacteria for this purpose. Microbes play a role in converting sand into sandstone, and so if you can speed up or catalyze that process in some way, you can speed up the aging and improve ground that way. I mentioned already you can do a removal and replacement, recompact it. Just be sure that you're actually improving it. Okay, there's a lot of removal and replacement, I think, of perfectly good ground just based on bad testing practices in Southern California. If you go do ModCal samples and predict that you're going to get a foot of settlement and then remove and replace, it's like, oh, well, have you really improved the ground? Got to be sure of that if you're going to spend the money to do it. There's deep soil mixing also. That's where you use these big metal paddles that get pushed in the ground, and instead of grouting or erosion grouting, the paddles mix up the soil with a cement material, and you can improve it that way. There's a whole bunch of other ones. There would be like stone columns. That's where you drill holes in the ground or insert a probe in the ground and compact stone in columns, and you can greatly increase the strength and stiffness that way. There's a whole bunch of other ways that you can improve the soil at a particular site to stabilize slopes. And I don't really have time to go through all of those. That could be an entire other class on ground improvement methods. So I think I'll end there.